Okay, so errors is kind of a mystifying topic. I remember being a student and finding that it very um, unclear, honestly. So I'm going to try to make this as clear as I can. So errors have to do with small changes that we can't predict, right? Small changes, we measure something and it's not quite right. So suppose we measure, and that's why it's related to differentials, because there's something that's not quite right. It's a small change. And so differentials work best when um, the changes in x are not very big, because then the tangent line is a good approximation. So let's go back to the beginning here. Suppose we measure a quantity x, and we determine that the true value is somewhere between x minus delta x and x plus delta x. In other words, it's a kind of interval where we think that the real value is going to be somewhere between the if we go delta x in that direction or if we go delta x in that direction. So the maximum error in this case is just delta x, right? That's the farthest away the truth could be. And the maximum relative error is the error divided by the value of x, which is delta x over x, right? Oops, delta x over x. So that's called the relative error. Okay, and there's also what's called the percent error. The percent error would be delta x over x times 100%. So that would just change it to a percentage. Let me make this a little bit nicer. So it's the error, the maximum error divided by x, which is that. Okay, now, so let's do an example. For example, if my height is h is 185 plus or minus a half centimeter, then the maximum relative error is delta h over h, which is 5 centimeters divided by 185 centimeters, which is 0.5 divided by 185, 0.02702, something. And the maximum percentage error is that same thing times 100%. So it's shift the decimal place twice, so 0.2702%. Okay, so far so good, right? Now, where we need differentials is if we measure something and it has an error, and then some other quantity depends on that first one. So for example, maybe the weight of a person depends on their height. And let's say there's a known relationship there. Then if the height is uncertain, then that makes the weight is uncertain then too. So how does uncertainty in one variable induce or lead to uncertainty in another variable or error in another variable? So here's an example. Suppose we measure the radius of a disk, and it's 24 centimeters. And we estimate the maximum error to be 0.2 centimeters, so plus or minus 2 millimeters. So in other words, imagine what this means. It means that the real area might be a little bit smaller, like this, or it might be a little bit bigger. So what is the plus or minus error for the area? That's what we're going to figure out. I know the plus or minus for r, but what about for the area? So given this, we can calculate the disk's area. It's pi r squared, so pi times 24 centimeters squared, which is pi times 24 squared, 1809.557 centimeters squared. So that's we would say our central guess or our best guess given the value of r. But now, what about the fact that if the radius varies by a small amount, we'll call that dr. So that's the change in, let's put it like this. So here's the graph. So we know that a depends on r. It's actually a parabola, right? A depends on r like a parabola. And here's my r. What if my radius varies a little bit? So I go this way or this way by an amount. Let's go this way, or I can go this way. This is the amount dr. If I change the radius by an amount dr, how much does the area change? The corresponding changes in A are well approximated by the differential, which is saying that delta A is approximately the same as dA. Remember, I said that's exactly the idea of linear approximation. Changes in A are approximately the same as dA, which is dA dr times dr, which is, what is dA dr? dA dr will be 2 pi r, right? Bring down the 2 pi r times dr. Okay, now we're somewhere. If the change in r, if dr is 0.2, then dA is 2 pi times, what is r? 24 times 0.2 centimeters, which is 2 times pi times 24 times 0.2, 30.159 centimeters squared. So what I end up with is a relatively easy way to estimate the change in area. So let's just think here for a second. What is the actual change in area? So the actual delta A would be pi r squared. So like if I increase the radius by 0.2, now I'm using 24.2 squared. And the old area was 24 squared. So let's just for comparison, let's work out what that is. So it's pi times 24.2 squared minus pi times 24 squared, 30.2849. And those numbers are very similar, very close. So they agree in the first two digits, and they disagree somewhat in the third digit. So that's about a less than 1% error, less than 1% difference. Okay, so that means that the differential approach gave us practically the same error as the exact approach, which is good. So that's why, and it's easier. Okay, so what is the maximum estimated relative error in R? The maximum estimated relative error in R is dr over r. Well, let's say it's delta r over r, which is the same thing as dr over r, which is 0.2 divided by 24. What's the maximum relative error in R is 0.00833, or 0.833%. This is where things get really valuable. What is the maximum estimated relative error in A? Maximum estimated relative error in A. So it should be delta A over A, but we do just fine approximating that by dA over A, which is 30.159 centimeters squared over A was 1809.557. So that would be 30.159 divided by 09.557, 016666, and that goes on. So that's the, which is 1.66%. Now that's interesting. Maybe you don't see it yet, but that's interesting. That's approximately double. That's very, very close to being double the relative error in R. Why would that be? Right? This is approximately double that. I can see that if I double this, I'll get 1.63, 1.66. Why would that be? There's a really important reason here, so let's look at that. Why is delta A over A approximately double delta R over R? Well, let's see. So we know that dA over A would be what? It's the derivative, dA dr. Let me write it the way you're used to. So it's the derivative dA dr times dr. That's dA divided by A. Right? So I've just substituted in differential dA is dA dr times dr. What is dA dr? It was 2 pi r times dr. And what is A? A is pi r squared. So now if I do a little bit of simplification, little canceling, just because that cancels out. There's the 2 there, right? So it's 2, I don't need to change color here. It's 2 times dr over r. And just, I can manipulate that very slightly a little bit more. That's 2 times dr over r. So this is the maximum relative error in R. This is the maximum relative error in A. So the maximum relative error in A is just double the maximum relative error in R. Double because of this 2. Interesting. So where did that 2 come from ultimately? If you think about it, where did that 2 come from? It came from this 2. So when I squared R, I doubled the relative error. Let me see if I can get that. So when I squaring R doubled the maximum relative error. So maybe you can imagine, what if I cubed it? What if it was R cubed? Then I would triple the maximum relative error. So we're going to see an example like that in a second. Okay, so let's see, this is our last example. And then look, we're done that whole note package of 31 pages. Wonderful. Okay, last example. Now, okay, so I have to take back what I said. I said we were going to do a 3-dimensional one with cubed, but we'll have to save that for the homework. I forgot that I removed that one. So this one's just as useful. Okay, one side of a right triangle is known to be 20 centimeters, and the opposite angle is 30. Okay, let's see here. So one side is known to be, a right triangle is known to be 20 centimeters. And the opposite angle is measured as 30 plus or minus 1 degree. Use differentials to estimate the error in computing the hypotenuse. Let's call that h. That's the hypotenuse. So let me call this angle theta. We need a name for that. And this side, the side here, we're simplifying a little bit. We're assuming that's exactly true. So we're pretending for a moment that there's no error in that measurement, which is of course not realistic, but we have to start somewhere. So assume this is exactly 20, whereas this angle, it's 30 plus or minus 1. So the question is how much error could there be in h? So the first thing is, well, what is h? How would we find h? So let's see, how do you relate these? So that would be sine of theta is opposite over hypotenuse. So that's going to be 20 over h. So if I solve for h, let's see, that would be h is 20 divided by sine, which is, that's fine as it is, right? So imagine this now. What happens if theta was 31 degrees instead of 30? What happens if it was 29 degrees instead of 30? That would change the h, right? So what we're imagining is, imagine what happens if theta changes by up to 1 degree either in either way, like adding or subtracting. Then here's what we would say: the change in h induced by that, is approximately dh. That's linear approximation. dh is dh d theta times, dh d theta times theta. Oops, no, that's not right. Times d theta. Now, what is dh d theta? Well, let's write it out using our rules. So dh d theta would be the derivative of 20 over sine theta times d theta, where now this d theta is going to be 1 degree, right? Because that's the maximum change in theta is 1. So how do we differentiate this? It's the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared times d theta. So what do I get? 0 minus 20 cosine theta over sine squared theta times d theta. So the change in h is approximately this expression. And the question was, estimate the error. So what we want is the absolute error here. That's approximately equal to. We'll do the relative error in a second. Still having problems deleting. It's funny. Why is that? Okay, that's okay. So if theta is 30, then that means that delta H is approximately minus 20 cosine of 30 degrees over sine squared of 30 degrees times d theta, which is, what is cosine of 30? Let's see, I find it helpful to draw the special triangle when this kind of thing comes up. This is 1, 2, this is root 3. So cosine of 30 is root 3 over 2. And sine squared of 30 would be 1/2 squared d theta. So delta H is, let's see, that would be minus 10 root 3 divided by 1/4, which is times 4. Okay, so we have a connection here between d theta and dh. So that means if theta changes by, and remember that delta theta is the same as d theta. They actually mean exactly the same thing. So if theta changes by 1 degree, then h changes by approximately minus 40 root 3 times. Oh, I just realized something important here, which is that we have to use radians for this part. Because the derivative, okay, let me tell you in a second. What is 1 degree in radians? It's going to be times pi over 180. So it's just pi over 180. Why do I have to use radians? Because the derivative of sine theta is cos theta only if theta is in radians. So where did we assume that? So right here, in order for this derivation to be correct, I have to sort out this computer issue. In order for this derivation to be correct here, it had to be in radians. Okay, it doesn't affect any of the rest of it. Okay, we're okay. So here we are. So that's going to be pi over So that's pi over 180 there. And what do I get? So minus 40 times square root of 3 times pi times pi divided by 180. Negative 1.209. Negative 1.209. What would the units be here? Change in height would be centimeters, right? Centimeters. That's what we're using. Okay, so the maximum error in height is approximately negative 1.2 centimeters. Now we're going to do the relative error. So the relative error would be just that divided by h. Now, what is h? We didn't actually work that out, right? H is 20 over sine theta. H is 20 divided by sine of 30 degrees. Which is 20 over, what's sine of 30? Is half. So 20 divided by half is 40. So h is 40. Okay, so we get the relative error divided by 40, negative 0.03. 022. So that's the relative error. Now, that's true, and that's good. But I wanted to show you one last way to get this, which is avoids all the numerical details. We're going to say that delta h over h is approximately dh over h. And what is dh? dh is the derivative, dh d theta, times d theta over h. And let's calculate this. dh d theta. We have that somewhere here, don't we? dh d theta would be this stuff. Oops. It really doesn't want to keep up to me here. dh d theta is minus 20 cos theta over sine squared. Okay, I think I've maybe corrected that a little bit. So what's the derivative? It was minus 20 cos theta over sine squared theta d theta. And what is h? Let's use the formula for h. H is 20 over sine theta. So let me continue this way. This is sine squared. So if I'm really careful, I'll get to the end here. Dividing by a fraction is the same as multiply by the reciprocal. So now this 20 is gone. This sine theta cancels that. So I get negative cos theta over sine theta d theta, which maybe I'll write this as negative 1 over tan. Now, what that means is the relative maximum error, or the maximum relative error, I should say, in h is minus 1 over tan theta times d theta, which was 1 degree in radians. So what is minus 1 over tan 30 times pi over 180? What is tan 30? I know that. I can do that, right? Tan of 30 is 1 over root 3. So it's negative 1 over root 3 pi over 180, which is negative root 3 pi over 180. What do we get? What is negative root 3 times pi divided by 180? Negative 0.03022. So that's the same thing as we got before. Same as before. So it can be helpful to work with the formulas, and then in that case, let me just summarize what we had here. So we found that dH over h was approximately 1 over tan theta d theta. So that would, in this case, that would tell us the relative error in h for any angle and any change in the angle. So that could be useful for more involved error analysis. Okay, so let me just quickly summarize what we did. So we used differentials to represent the changes in the function along the tangent line, which is approximately the same as the changes along the function itself. And working with differentials is, believe it or not, easier than working with the functions themselves in many cases. All right, we'll leave it there. We'll see you in the next video.